Ok, so vou dar curso de I'm supposed to speak in English. I'm going to speak in English. I can answer questions in Portuguese. It's been many years since I taught a course, like a regular course in Portuguese. So I'm not 100% familiar with some of the language that people use in mathematics. So, but I know most of it in Portuguese. I can certainly speak in Portuguese. Okay, so I had a lot of difficulty making up this course. I was hoping to make slides for all the lectures, have it very organized, and it became extremely difficult to do that. So, and try to do a very linear course where you learned this and you learned that. So more or less yesterday I gave up on that, and I tried to reorganize the course a little differently. So I'm going to sort of touch on different topics, and I'm going to assume you kind of don't know anything, and then sometimes I'm going to assume you know something. And we're going to kind of go back and forth with this learning process. And a lot of the ideas in my course probably are more topological in nature than other courses, so I am going to emphasize some topological ideas along the way that maybe is a little bit different than a regular course you've had before. And I found this way of thinking very, very helpful. There are lots of unsolved problems about the topology of constant-mean curvature surfaces and how they live in the space in a topological way. And not all the sub-course is going to be about minimal and constant-mean curvature surfaces. Some of it will touch on broader examples, like maybe positive mean curvature or anyway, different properties, okay? And we're going to be focused mostly in studying surface geometry in three-dimensional Euclidean space, but I'm also going to go into the other Riemannian manifolds. For example, hyperbolic three manifolds. Homogeneous three manifolds in general are going to be sort of a natural ambient space in which to study the geometry of surfaces. So the focus at the beginning is mostly Euclidean space, but later it kind of goes more into three-dimensional manifolds, the geometry. So maybe even think of trying to understand three-dimensional manifolds by studying surface theory in them. I mean, it goes both ways. So, okay, so the first lecture is partially based, I would say maybe a fourth of it is based on a very nice lecture that Giuseppe Tignaglia gave to some students. So I found it very, very nice, and kind of get a feeling, get your kind of teeth into the subject, get a feeling a little bit. What are the interesting problems? How do we perceive those problems? How do we look at the subject? What's the history? Who were the people that made important contributions to the subject? Just so that get a little classical feeling for the subject. And so he gave a very nice lecture. So partly my first lecture is partly based on some of the slides that he produced to give this sort of very nice presentation of what is the theory of minimal surfaces. And many of the figures I'm going to draw, I don't give credit to, but they are done by Matthias Weber. So he does these amazing computer graphics pictures of minimal surfaces. I used to do them, but he came along, he does them much better, so I kind of got out of that subject of making minimal surface, making pictures. So, but you can see already, here's like a round sphere. Sphere is one of our examples, constant mean curvature surfaces. We have this spinning helix, so we see something like a helicoid. It's kind of a screw motion, sort of something like line segments, like molecules or something. And of course, we have soap bubbles, and that's going to be also a theme in my talks. Okay, so just some of those really basic things that I'm going to talk about. I'm going to talk about more than these things, but just thinking in terms of definitions, fundamental for today's lecture is I'm going to be looking at surfaces in R3, and I'm going to try to be analyzing certain invariants associated to those surfaces, sometimes associated at each point on the surface. And so one of those invariants is the genus. We're going to be talking about the genus. Space of ends, I've got a feeling I probably will not conclude. I'll probably start talking about this today, but the space of ends is really something most mathematicians don't know very much about. And so I really want you to get a good foundation on what it means to be an end of a surface. This is just an abstract surface, a connected surface. What are its space of ends? What's the topology on the space of ends? It turns out there's a natural topology. I was going to write up slides about this. Like I say, it's very time-consuming to make most of these slides. This typical slide takes about 45, 50 minutes to make, and there are probably a whole lot in this talk. So sometimes I kind of gave up. I was going to do this yesterday, do this presentation of space of ends. I just ran out of time. Okay, so we have completeness. Hopefully you're familiar with complete Riemannian manifolds, surfaces, complete metric spaces. Properness, that's a concept that's closely related to completeness, and I'm going to talk about that quite a bit. So a lot of the outstanding questions about minimal surfaces in R3 are under certain hypotheses. Are they, when they're complete, are they proper? And that when they're proper, we have many more tools to understand the surfaces. Lots more could hold. Lots more theorems or special theorems hold only when you're proper. Gaussian curvature, again, I hope I'll define it, but hopefully you know what it means. Mean curvature, norm of the second fundamental form, it's just a way of measuring how curved a surface is. So a big norm of the second fundamental form means it's very, very big, very curved, somehow very contorted in its local geometry. Another very important function for my course will be the injectivity radius function. So we'll talk about that. And the injectivity radius of the surface. So that's related to this injectivity radius function. So when something's well behaved, somehow its injectivity radius function stays, it's always bigger than 0, bigger than some number at each point. So anyway, we'll be talking about that. And the course, I have the book here, I think, but anyway, the course is based in part, just part of it's based on this survey and minimal surface theory that I wrote with Joaquin Perez. I have a copy of the book. You can go to his website and just download a free version if you want, Joaquin Perez. Okay, and like I said, many of the things I'm going to talk about apply to three manifolds. Okay, so just talk again, just sort of this very general sort of idea where I'm heading. So for today, I'm talking about the genus and the space of ends, classification of compact and non-compact surfaces, completeness versus properness for surfaces in R3. These basic definitions, we talked about them before. Injectivity radius function, injectivity radius. I'm going to give lots of examples. We're going to see lots of interesting examples. I mean, right away, we're going to be seeing lots of interesting examples of surfaces. Most of the slides you're going to see today have a picture on them. So you're going to see a surface right there on that. Okay. So lots of pictures, lots of examples. Okay, and it turns out it's important. I said classical examples. You say, well, these things are all known. Well, it turns out that classical examples actually provide us with very important tools for understanding geometry of surfaces in three manifolds. So it's very important to understand what are the classical examples. They play a much more important role than most people could imagine. And hopefully you'll start seeing this when I talk about parking garage structures. Okay, so another thing I want to talk about in this first talk are these sort of classical minimization questions like Plateau's problem, the isoparametric problem, properties of solutions of these minimization problems, area and volume kind of questions. And there are various different kinds of questions. One of these questions are what are called isoparametric problems in three manifolds. Okay. I'm also going to be spending some time talking about laminations. So they're kind of a generalization of surfaces, okay? And they also kind of a specialization, sort of a foliation is kind of in that sort of realm. If you know what foliation is, like a foliation of R3, you can take by parallel planes. You can decompose R3 into parallel planes, or you can decompose the plane into parallel lines. Or you could take any non-zero vector field on the plane and you can look at the integral curves. There are lots of foliations of space. And some of these foliations may have constant mean curvature leaves. In other words, the surfaces that represent some part of the lamination or foliation might have constant mean curvature. So we're going to be looking at what are called minimal and H laminations. A green H in my course will usually mean constant mean curvature H. H is going to be a number. Okay. And I mentioned before, a reasonable part of this first lecture is actually about parking garage surfaces and structures. It turns out that's a fundamental structure that appears throughout the theory. It turns out that most people that work in the subject really know very little about this, and to their own detriment. So you're going to find out right away something your thesis advisor might not know, but which is really, really basic and important. So we're going to be looking at this, and I think you'll understand what these structures are, at least get an idea about it. And I'm around, so you can also ask me after the class, and maybe we can even meet up sometimes, and we can talk about. You have questions about things. Okay, and right, and then we have some classification questions. So one of the important problems in the subject, so these classical, important, fundamental questions are classification. What are all the surfaces with some properties? Can we write them all down? How explicitly can we write them down? Can we just prove uniqueness, or we can actually analytically present these examples? So both kinds of questions appear. Sometimes it's impossible to analytically prove things, like write down formulas, but we can still prove maybe uniqueness of the examples, okay? Or maybe there's a family of examples. We can study the moduli space of the examples. And these are really important basic questions. All these things I'm going to talk about somewhat today. So at least at the beginning, I have these nice slides, and I'll use them as a crutch for my lectures. Okay, so we have our sort of standard picture of a surface in R3. We have its unit normal field. We have under parallel translation, the tangent space at a point can be identified with its tangent space on the sphere of the unit normal field. So I'm assuming right now, say the surface is oriented, we have this normal field on it, okay? And because we can identify under translation the tangent space of the sphere, and we can take the derivative map to here, and we can just translate back, and we can think of this as a linear transformation at each tangent space, and that's called the shape operator. And from the shape operator, we can get certain invariants. Again, I assume most of you people know these things, but I don't know. I don't know exactly everybody in this class. So, okay, so we have, for example, we have what are called the principal curvatures. So we have, for example, we have our surface. And we're going to be talking about normal curvature in a second. So you have the normal field. And if I take this plane, a vertical plane that contains the unit normal, I'll get a trace curve on that. And that has what's called a normal curvature. That curve has a curvature sort of, well, in this picture, it looks like it's pointed in the direction of the normal vector. But it could be, of course, if I take a plane like this, then it will go the other way. So we have the principal curvatures, and these eigenvalues of A just turn out to be the maximum and minimum of the curvatures, where the minimum might be a negative number. So we have a notion of which way the curvature goes. Do we curve in the direction of the normal vector, or do we curve away from it? Okay, and then we have the Gaussian curvature function on the surface, and that's just the determinant of the shape operator. And it's very important to remember that the determinant of a map is the Jacobian of the map, and that just tells you how area changes. So when you go back and look at this this last map, you take a little piece of area here, a little teeny like disk here, and you look at its image value. It gives a little surface around, say, the North Pole in this picture. And the determinant tells you how you stretch area. So we can identify, for example, the integral of the Gaussian curvature, or the absolute value of the Gaussian curvature, with the area of the Gauss map. In other words, the integral, we integrate the Gaussian curvature over the surface. We find out we cover up the sphere with a certain amount of area, and maybe that's a finite number, in which case we get an interpretation, a geometric interpretation of the Gaussian curvature when we have a Gauss map, okay? And we have another important invariant, which is telling us how much the surface curves. So if the normal curvatures are all small, then in absolute value, then this number is going to be small. That means it looks like a flat graph over its tangent space. So locally, you can look at the tangent space on the surface, and you can think a little part of the surface is a graph over its tangent space. Well, if it's a very flat graph, then that corresponds to this number, this norm of the second fundamental form being small. And another crucial equation that we have from classical geometry of surfaces is what's called the Gauss equation. And this is for R3. We have 4 times the mean curvature squared, that function squared, is equal to the norm squared of the second fundamental form plus 2 times the Gaussian curvature. And of course, immediately you get some certain kinds of relationships if you knew certain things. So if this is 0, okay, over here, then you can see that the Gaussian curvature is going to be non-positive. That's one consequence of this equation. Or, for example, if the mean curvature was 1 at a point, then you get an estimate for the then we get Then we get an estimate for the Gaussian curvature. So it turns out if the mean curvature is bounded, then the Gaussian curvature somehow is big, if and only if the norm of the second fundamental form is big. So big Gaussian curvature means big norm of the second fundamental form. They become the same thing as long as the mean curvature is bounded. Okay, so somehow these are different ways of measuring how the surface curves in space. So at least when this is a bounded function, these two being bounded are essentially equivalent sort of questions. And that, because we talk about curvature estimates, and when you go to somebody's talk, a professor's talk, and they say curvature estimates, it's not clear what they're talking about. Are they talking about Gaussian curvature estimates, or is the norm of the second fundamental form estimates? And it just depends. If they probably aren't saying anything at all, then they're saying curvature estimates. They probably mean this estimate, norm of the second fundamental form, I guess. Anyway, so this is just, again, a little bit more interpretation of things. So if you have a surface and you look at the mean curvature at a point, we actually like to think of mean curvature vector. So if you don't have the surface being oriented in space, if you don't pick a normal vector field, you could still try to make sense of the mean curvature. And that's sort of a way to do it. You could just take 2 planes, 2 orthogonal planes, look at the curvature of the corresponding normal those curves that are in those 2 planes, and just, so for example, this curve, here's the curvature vector for Ed. If I took this plane, then it turns out its curvature vector is going to be pointed down somewhat. And if I add those 2 vectors, I get a vector. And that's called the mean curvature vector, somehow the natural mean curvature vector. And the length of that would be the mean curvature. I think mean curvature divided by 2 might be. Right, so anyway, so I have this factor of 2 here. So we have, of course, these simple examples. This has got curvature 2. Along the straight line, you have curvature 0. So this would be, along the straight line, you have a mean curvature of 0. So let me go with this in mind. Right. Let's just backtrack for a minute, and I'm going to do a little something on the blackboard. So this goes back to something I did many, many years ago. It's something that's very simple. It brings us back to things that probably are familiar to most people. A little bit of Morse theory. Okay, so I'm going to try to try to use some of these properties here. So let's see. Right. One of the things that are very important in this subject is when you have two surfaces. I have a surface. I'm going to draw it one-dimensional. I have a surface here. And I have another surface that lies on one side and intersects at a point, OK? And I want to say, well, how does this surface somehow induce something about the geometry of this other surface? If I know something about how this surface is curved at this point, this surface lies on one side of it, what can I say about the related geometry of the second surface at this point? So let's suppose that at this point, the mean curvature of M1, mean curvature vector at the point, is like that. It kind of looks like it in the picture. It's curving toward that direction. Then how can I get a comparison for the mean curvature of the second surface at the point? Okay, and so it turns out you can see I could take the same planes that give rise to the mean curvature vector here, and because this is on this side, I end up getting an inequality on the mean curvature. So if you were in the plane, these were just curves, it's clear that the curvature of this curve is at least as big as the other one. So bigger than or equal to HM1 at the point. Okay, so that's called the mean curvature comparison principle. Okay, so if you're on the mean convex side of a surface, the mean curvature point of this, and you take a surface that touches it at a point, its mean curvature is at least as big. Okay, and if you think of these as functions defined locally around the point, and somehow these functions, you have to write them as graphs and stuff like that. You have an inequality like this, then it turns out, anyway, for example, you have constant mean curvature. Suppose you had constant mean curvature and you had this picture, then in fact what you end up seeing is that the surfaces agree in a neighborhood of the point. You have a sort of a maximum principle. This inequality, when these functions are the same, you have to make sense about what the same means, like constant value, that would make sense being the same, then in fact this inequality, this gives you that the surfaces in fact agree in an open set. So it's very, very important, okay? So I'm going to use this idea to prove something basic about the geometry of surfaces in R3. So, I don't know, it's a theorem or a proposition or a lemma or whatever you want. It's nothing very important. So I look at a surface in R3, and it's going to be what's called proper. Okay, everything's smooth in my talks. So smooth surface, proper. Proper just means in a big ball, you see a compact part of the surface. And I'm going to assume it's non-compact, connected, like a plane, for example. A plane would have that property. Okay, so now I'm going to make an assumption about for example, it's Gaussian curvature. Okay, so suppose the Gaussian curvature function of this surface is less than or equal to 0. Then what can I say about how it separates R3 into two pieces? So if you have a surface in R3 that's properly embedded, it always separates into R3 into two components. So let these be the closed components of M in R3. In other words, you're taking R3, you remove the surface, you get always two solid regions, and I look at the closures of those regions. Okay? So what can I say about these domains? For example, are they what are called open handle bodies? So do they look like somehow something one-dimensional, some kind of one-dimensional aspect to them? So the open ones are actually, so the interiors of these are going to be open handle bodies. Open. Okay. In particular, the fundamental group of these solid regions are always free groups. Free groups on maybe an infinite number of generators, maybe if you had a plane, maybe they're simply connected regions, so free group on zero generators. So anyway, we want to kind of see this. And I just want to use this very simple, sort of kind of like a comparison principle we had before. So just to do the picture, so here's, suppose this is N1, here's the surface. And just for making it easier, suppose the surface goes through the origin. You could always translate it so it had this property. It's not going to change our question, right? So, and here's our region N1 on this side. Then I want to think in the terms of Morse theory. So I'm going to look at the distance function, the radius function in R3. So that takes R3 to 0, infinity. And I just want to try to imagine what happens to this region as I take different values of R, as R changes. So initially, of course, I start off with I'll kind of draw it like a ball. So initially, as I kind of do this exhaustion of the manifold by ambient balls intersected with it, then what happens to these things? What happens to these balls? Well, I'm going to ignore the being disconnected for the moment. So we come up to maybe a critical point, something like this. So people who are familiar with Morse theory have seen this kind of picture. And what kind of topology do I have here? So I have a ball, and then I have, so this picture, I have two disks. So things can only change in the topology of this domain somehow when I have a critical point for the distance function. That's the only time anything can change. But notice it doesn't always change. If I had an index 1 critical point like this, nothing happened. Okay? And that's because the normal vector, think of the inward normal vector to the surface, is pointed oppositely to the level set of the two-sphere. So we have the normal vector to the two-sphere, we have the normal vector to the solid region, and if they're pointed in the same way, nothing happens when I pass a critical point. You can just draw your own little favorite picture, you can see that. But if I go a little higher, like this, right, then it does change. So here the normal vectors are pointed in the same direction. The normal vector to the interior of the domain points in the same direction as that. So these are kind of analysis of what happens at an index 1 critical point on the surface. So there's an index 1 critical point for this Morse function. Think of it as a Morse function. Translate the surface so it's in general position with respect to somehow this R function. So you can, okay, so index 1 critical points, we understand exactly what happens. Here, nothing happens to the topology. And here, what happens is you attach a solid one handle. Okay, so I attach a one handle, which makes one more generator in the fundamental group. So if I only have index 1 critical points, it's clear that I've made what's called an open handle body. So then you have to deal with other kind of critical points. I could have had let me try to draw it. I could have had a local minimum on the region, right? So a local minimum will just then create more of these balls, and I'll just also follow what happens. And I get to a critical point like this, they just join up. So it turns out that these don't really do anything very interesting with respect to our problem. The problem could be a critical point like this. Maybe the manifold's over here, and when I come up here to a point like this, I attach a two handle, right? I'm going to attach a two handle, and the topology will change. But I can't do that if the surface has non-positive Gaussian curvature, because the related sphere here, that would mean the surface was inside of a sphere of constant radius here. Well, the Gaussian curvature, the second fundamental form here is a sphere is just like 1 over r, 1 over r. It's positive. So you can see that the normal curvatures of this surface have the same sign, and therefore the Gaussian curvature would be positive. But we said we had non-positive Gaussian curvature. So you don't get any critical points on the solid region corresponding to attaching two handles. That means I have no relations. Two handles are what change the relations in the fundamental group of what I've made so far. So as long as I only attach one handles, I don't change the property of having a free fundamental group or having this sort of topological picture. Okay, so anyway, that's the idea. Okay, now we just had that other slide. We're talking about what the mean curvature is. Notice that what's in different condition than this that will make the proof work the same. Remember, we just looked at what was called the mean curvature comparison principle. So I want to make sure when I take this Morse function on the solid region, I don't attach any two handles. And remember, the picture of a two handle was I have a two sphere, and I have my domain having somehow a local maximum on it. This would be like the domain. As long as I don't attach any two handles. Well, if I have this picture, by the mean curvature comparison principle, the mean curvature of this surface has to be at least as big as the mean curvature of the sphere. So instead of saying this, I could put a condition which is the mean curvature function of the surface is an absolute value is less than or equal to 1 over r. So if you're at a point on the surface, if you do it at a point P, then 1 over the norm of P. So that would be a condition which, again, guarantee that you don't have any of these, any kind of two handles attached. So as long as you have a properly embedded surface in R3, whose mean curvature, for example, goes to 0 reasonably quickly, and it's not too big anywhere near the origin, then you have this nice decomposition of the space. Okay? So that's a very interesting, in particular, if it's a minimal surface, I automatically have this property. So if I have a properly embedded minimal surface, minimal corresponds when this function is identically 0, then I'm automatically, I have non-positive curvature, as we mentioned before, but I'm going to have this nice property. Okay? There was something else I wanted to say here. Right, so how is this related to other more deep questions? Deep questions are ones which we puzzle over. We don't know the answer to. They're basic questions. So you could ask, here's an example question. If you have a properly embedded h is identically equal to 0 surface, and I'll just give an example. We're going to be talking about these in a minute, a little while, but we're going to be talking about what ends are. But suppose it has what's called one end. A plane has one end on it. A cylinder has two ends on it. Okay, so if it has one end, even if it has infinite genus, it turns out that it's somehow standardly embedded. So these ideas lead to questions like this. Okay, standardly embedded. Okay, standardly embedded means there's only a way to embed the surface. I know how it's embedded in space. So in particular, if I had two properly embedded minimal surfaces in R3 of infinite genus and one end, then there's a diffeomorphism of R3 that takes one surface to the other one. There's only one way to put it into space. Now, when this has genus finite, then that's relatively easy to do. So in other words, just this knowing that you have an open one-handle decomposition and knowing that you had finite genus and one end. So let me draw a picture. Suppose we have, so here's some genus, right? And then after some point, you don't have any more genus. So after this, I have like a cylindrical end. So this is the picture. If I have genus finite, then it's not too hard using three-manifold theory to actually prove this thing I just said. If you have infinite genus, it becomes quite deep, the question. So, but if you have one, then you can relate this to what are called Heegard splittings. splittings of R3, or even of a ball. So you can imagine a ball. You have one boundary curve. If you have one boundary curve and the surface inside the ball separates each of the regions into handle bodies, then a theorem of Wallhausen implies there's only one way to topologically embed it in this ball. So knowing handle bodies sometimes tells you how the surface is actually embedded globally inside the region. So this is the way you would embed a finite genus, say genus 3, surface inside a ball with one boundary curve. This is the only way to do it if you knew each side was an open handle body. There's only one way to do it. Okay, so let me just try to think of another place we could apply the same idea, hyperbolic free space. So I'm going to just tell you a little bit. I'm going to keep coming back to these things, but for somebody who knows something about hyperbolic space, so we have, for example, in hyperbolic free space, we have a ball model. And you could think of, here's the origin, the center of hyperbolic space, and you have a nice decomposition by, again, spheres of radius r in hyperbolic space. Now, the property of spheres of radius r in hyperbolic space is, for example, their mean curvature is always bigger than 1. Okay? So the same argument we used over there shows that if we had a surface in here, its mean curvature function was less than or equal to 1, maybe it has lots of ends on it, whatever. It always decomposes hyperbolic space into two one-handles, open one-handles. Okay? It doesn't mean it's standardly embedded. Okay? There's a famous conjecture of mine. I don't know how famous, probably not that famous, but I'm guessing nobody in this room knows it but me. But there's a conjecture that appears in various locations that would say that if you take a surface properly embedded in hyperbolic free space, whose mean curvature is exactly 1, then you take two such surfaces, there's a diffeomorphism of hyperbolic space that takes one to the other one. In other words, perhaps, that's a deep question. Lots of related questions to that question. But perhaps, for special numbers, the mean curvature determines how the surface is actually sitting globally in the space. And all this came just from the definitions, basically, just right at the beginning of the subject, the definition of what the Gaussian curvature is, what the mean curvature is. You get these very nice nice sort of results. Okay, so of course, so we have our classical examples. We have, keep in mind, a sphere of radius r has mean curvature 1 over r. Okay, the normal curvatures are each 1 over r, and you have two of them. And you divide by 2, you get the mean curvature. And we have the cylinders, of course, another one of our great classical examples. It's kind of interesting non-compact example of constant mean curvature. 1 if you make the radius of the circle 1/2. So that's a good example. Okay, so then we're going to get to our first sort of definition. What is a minimal surface? Again, I hope most people have seen this kind of stuff before anyway. So an H surface is a surface with constant mean curvature H. When that H value is 0, we call it a minimal surface. Okay? And it's the mean curvature vanishing. We have what's called the first variation formula. It tells us, in particular, that with respect to variation, so if you take compactly supported, this means they vanish outside of a compact set. So if you look at a compact part of the surface, and for example, you look at variations so here's the boundary, here's the surface, here's the boundary of M, represented like 2 points. I mean, to do it right, of course, you'd want to make it be like a disk, maybe. Then we have variations, just means you do a deformation. Say, think of a normal variation. You don't have to do normal variations, but say think of normal variations. That's a natural thing to do. Just a family of perturbations of the surface with the same boundary values. Then as you go through that family of disks, in my picture I did it with disks, then you can look at the areas of the surface. You can take the derivative. You can think of area at time t. You can take the derivative, and that derivative is always 0. So that's the sense that we mean. It's a critical point to variations, compactly supported variations. And our key examples are the catenoid, and I'm going to talk quite a bit about problems related to the uniqueness of the catenoid today, and the helicoid. Okay, the helicoid, you take a straight line, you take a line orthogonal to it, and just rotate it constant speed as you go up. So those are sort of our two really important examples. Okay, so let me just explain a little bit about this. I mean, sure, everybody's wondered about it. Hopefully my explanation is as good as your own intuitive idea of why your soap films have zero mean curvature. So soap film, of course, is made up of water with other molecules in it. And the water molecules want to attract to each other, right? And they form a film that doesn't pop right away because you put some soap in it. Okay, so you have this sort of, the molecules want to attract each other, and they're pulling towards each other, but at the same time, you have to attach to the boundary curve. So there are these forces. This is caused by surface tension. And these forces pull in opposite directions. So when you draw your favorite picture of what you think is something of zero mean curvature, you have somehow, at a point, you're curving up, and then orthogonal to that, you're curving down. So think of these as principal directions. This is maximum of the normal curvature, the minimum of the normal curvature. Then the little molecules are trying to pull each other tight. And the forces, this pulling breaks up into two orthogonal forces. Okay? So these little molecules here want to pull the surface up. When they want to get together, they want to pull it up. And these here want to pull it down. They want to pull it tight down. And those forces have to cancel out because it's a physical surface. Okay? And those forces, though, are proportional to the principal curvatures, these normal curvatures. So for that reason, when it tries to pull itself tight, it has zero mean curvature. It's physics. It's physics of trying to pull yourself tight, and the property that forces break up in these kind of standard things into, you write down matrices, and they're symmetric matrices, and they kind of pull it orthogonally. Okay, so that's why. So this is definitely a slide from Giuseppe's talk. So we have this sort of like a bit wire. We have our soap film. We have Plateau, who has studied this question initially from a physical point of view. We have Lagrange. He's in this picture because he studied the equations that a graph of a function. You take, for example, a disk in the plane. If you have a minimal graph over it, he wrote down what are called the Lagrange equation for the graphing function. So, okay. So anyway, so that's why their names are here. So we have soap films minimize area among close nearby surfaces. Okay. It doesn't mean that they minimize globally. So we're going to be looking at an example. So here's kind of this picture. We have all the surfaces, and we have these sort of minimum places where you have a local minimum for your surface. Of course, the global minimum is sometimes called the solution to Plateau's problem. You might be looking for a surface of absolute least area. But you have soap films where maybe the surfaces have some kind of local minimum. They're stable. Okay, so here's a good example. Hopefully you've seen this before. If you haven't seen it before, it's enlightening. It's a particular simple closed curve in R3. So it's kind of like a circle, two circles this way, two circles this way, and you kind of join them up. So you got kind of like two circles here, and you join them up. So it's a simple closed curve in space. And we're going to see in a second, it bounds more than one soap film. And only one of these soap films, presumably, is the area minimizing one, the one with actual local area, global area. So we have this one over here. Notice it has somehow two big fat disks, minimal disks on it. We have, where's the other one? We have this one, which also has somehow two big horizontal disks in this case. And then we have this one, which definitely looks like it's better, right? That little strip going around, if the curved circles are close, has less area than the related big disks that you see. So presumably this is the one that has less area. Presumably this is the solution of absolute least area, but here are our local minimums. And you can see once a curve is curving reasonable amount, then you have this sort of property. So one of the big questions in the subject is, if you have a closed curve in space, whose curvature, its curvature, right? You integrate the curvature at each point, is less than or equal to 4 pi, then it bounds a unique orientable minimal surface. Unknown. We do not know if that's the case. We do know that all the minimal surfaces which that curve bounds are embedded. So we're going to be looking at problems like that as the course goes on. So if the curve doesn't curve too much, you don't have this property. This curve curves, I don't know how much it curves, but it curves kind of 2 pi, 2 pi, 2 pi, 2 pi, and 2 pi. That's 8 pi, maybe around 6.5 pi or something. It's reasonably curved. It's bigger than 4 pi. All right. Oh, well, I should have said, at least when you're in the disk case, a curve whose total curvature is less than or equal to 4 pi bounds a unique minimal disk. Okay, but if I start adding handles into it, can I add handles? I don't know. Okay, so now a lot of my lectures are very geometric in nature. So you look at the helicoid, what do you see? Well, if I looked at it sort of right, I would kind of see two what are called infinite staircases glued along a vertical line. So there's a sort of a vertical line. Most of this blue surface is one of the staircases. So here's the red staircase. There's the other red staircase. Okay, so you got blue staircase glued together with a red staircase along a vertical line. So I want that sort of point of view. This is not just a surface, but it's a surface that's made by gluing two other surfaces along a vertical line. And those surfaces are what are called multigraphs. They project, they're graphs over the xy plane, but they go spin forever and ever. So I do want that sort of point of view. And remember, these lines go out forever and ever, right? These lines will go out forever and ever. So you can view the infinite helicoid as being somehow a kind of like taking two infinite multigraphs over the punctured plane, these spiraling staircases, and then you glue them together along a straight line. You take one of them and rotate around that vertical line by 180 degrees. The vertical line is a line of symmetry. Okay, and so we're going to look at this sort of thing again in just a second. And there's our proof. It's supposed to be a proof. This is Giuseppe's talk. And there we go. At least you can see half of the helicoid is somehow stable, and can be realized as a soap film. Okay, so you just make a straight line going over. You take a helix going down, and then a straight line going over again. And you make that wire, and you dip it in soapy water. You always get the same thing. At least I always get the same thing. It depends on how big you make. If you make the wire big, it's not true. But if you make it like that, you see it. It's not too hard to see that surface is ruled approximately ruled by horizontal lines. Okay, so then we have Meusner, 1776. He went and he verified mean curvature being 0 means locally you are a minimal graph. You satisfy Lagrange's equations. So he connected Lagrange with a nice property of having 0 mean curvature. So we have Lagrange equations for graphs which are critical points to area or minimizing for area. And he connected that, and he showed that if the mean curvature is 0, then you automatically are locally area minimizing, locally minimal graphs. And therefore, he made that connection. And you can check why, for example, does the helicoid have 0 mean curvature? Okay, suppose I knew it was a soap film. Yeah, I had 0 mean curvature, but I guess I want to go in a slightly different direction. So if you're in an ambient space, so if you're in, think in terms of a three-manifold. If you're in a three-manifold where you have lots of symmetries, so we're going to be looking at mainly homogeneous manifolds. But if I have a ruled surface in it, so think of a part of the helicoid. Okay, a ruled surface in it, and if rotation by 180 degrees around a line in the surface is a symmetry of the surface, then automatically its mean curvature at each point will be 0. And that's because you'll flip. You have to look at the average of the normal curvatures, and you rotate around a straight line, that changes the normal vector. So whenever you have a ruled surface and reflection across the straight line of these geodesics on the surface, right, if you can rotate around a line, then that is a geodesic. Fixed point of its symmetry is a geodesic. So anyway, so there are other ways to see that we can make surfaces sometimes in three manifolds which are ruled, and rotating around those, the rulings in the surface are ambient isometries. Automatically, that surface will have be a minimal surface, just because it flips the mean curvature vector. Leaves the surface invariant by an isometry, right? Ambient isometry. Okay, so now these are just some nice pictures. Try to get, again, a feeling for what, where these surfaces came from and so forth. So Archimedes used this kind of thing to pump water. So you can imagine turning that, and it will just pull the water up, okay? All right, so here's where we're going to get into some of these, I'm not sure what time it is, some of these more delicate problems. This is going to lead us to what are called parking garage surfaces. So you might think, well, what is this picture all about? Well, it's actually kind of interesting topologically, geometrically. Okay, so you have this Archimedes idea. You have these somehow like a helicoid, and it spins, and it pumps water up. And suppose this one spins the same way as this one. It's a little hard to see if that's the way it goes. But if they spin the same way, maybe that's what we have here. If you look at this carefully, you probably can't see it as well as I can on my laptop. But these two things that pull the water up, those screws are oppositely handed. Okay, so that means one is going like it looks like DNA, and the other one looks like a mirror image of DNA. So you can imagine something like that. So somehow we have like a helicoid one side, but maybe a helicoid spinning the opposite way on the other side. And you could imagine filling in this picture by horizontal surfaces in between. So we have somehow two helices which go down here. We have this sort of strip that spins, another strip that spins the opposite way. And you could imagine maybe these could connect up by multigraphs. We could connect everything up, and it'd be part of what's called a parking garage surface. So that's this kind of picture here. So this is a picture of what's called a parking garage surface in R3 with two oppositely oriented handles. So the picture is I have, I guess, a right-handed helicoid here. I have a left-handed helicoid spinning the opposite way there. And somehow I can fill in them as part of a global, properly embedded surface in R3, which is horizontal away from these helicoids. Everywhere else, it looks horizontal. And when you do that, you can see that when you do that, you always make somehow there are two surfaces in space that are like horizontal multigraphs, and they get glued, in this case, along two lines, two vertical lines. The helicoid we have two spiral staircases outside of a vertical line. In this case, we have the same kind of picture outside of two vertical lines. Okay? And a very interesting thing happens, and it's very important for what I'm going to be talking about. The helicoid itself is an example of one of these parking garage structures. or surfaces. It has the vertical axis, which is called its column. It's got one column. And outside of that, I see these two spiraling multigraphs. Somehow one oriented up, one oriented down. Okay? So when I do that, so a helicoid is an example of one of these parking garage structures with one column. This is a picture with two columns. Now, if you take a helicoid and you homothetically shrink it, so you just take it, so here we are, we have our helicoid. Okay, so we have our helicoid. Away from the axis, it looks very, very, as you go far away in the axis, it looks very, very flat. If you get far away from the axis, it looks very, very horizontal. Here, of course, it's curving. But when I do a homothety, I bring what's very far away from the line closer to the line. So here's the origin. And I'm up here. Well, I'll bring it towards the line. Of course, I'll also bring it down a little bit. But because it's very horizontal here, normal vector is almost vertical here. When I keep doing these homotheties, I keep shrinking and shrinking and shrinking, the distance between these sort of multigraphs goes to 0, and they become more and more away from a very small neighborhood of the vertical line. They're becoming just horizontal, and that converges to a foliation of R3. So we can see that even though we have minimal surfaces, it's very natural, a sequence of minimal surfaces may converge to a foliation. And we're going to be trying to understand that as well. I don't know if we'll get to it today, but we're going to be understanding that as well today, trying to understand that concept. So this is very, very important for us, okay? So we can imagine sequences of minimal surfaces converging to parking garage structures in R3. So imagine a sequence of minimal surfaces converging maybe instead of to a foliation of R3 with one axis, like in the case of the helicoid, maybe it converges to foliation of R3 away from two vertical lines along which it looks like helicoids, very homothetically shrunk helicoids. So that's one of the key structures that minimal surfaces, limiting structures that minimal surfaces have in three manifolds. Okay. So here's just this sort of picture. Again, you see these, lots of multigraphs. So what's supposed to communicate. And here's just the this sort of question. So then the question comes at what's the topology? Suppose these two columns, suppose the spinning is, maybe I should make one more explanation here. Let me go back to that picture I had before. So imagine you had a helicoid over here, and you come here and I have a vertical plane. So how does a vertical plane, and we have all these sort of very horizontal parts of the surface, how does a horizontal plane intersect parallel to the axis of the helicoid? How does it intersect the helicoid? Well, it intersects in almost horizontal lines, right? The curves that are asymptotic lines. So in here, I'll just see lots and lots of lines in this plane. And if I reflect across this plane, then I'll make one that spirals the other way. So that's one possibility. You just take this picture of a helicoid, take everything that lies on that side, reflect across this plane, make this other surface, and just, of course, smooth it off here, then you'll see a parking garage structure where we have opposite spinning, like on the red surfaces. So then this sort of picture where the spinning is opposite. So in order to pump water, this goes counterclockwise. This goes, which way is that? It depends on how you look at it, up. Anyway, it spins the opposite way of the other one to pump water. So that's this picture. But we could also just glue, you have the same picture over here by another parallel plane. We just kind of translate that picture over here. So now we're spinning the same way. So the interesting question is, what happens, what's the topology of that surface? I certainly have a surface. How can I describe its topology? Well, this slide is supposed to tell you something about it. So the left-hand side, where they're spinning the same way, you end up with a surface in R3 with one end. So that's a little abstract at this point. What does one end mean? But anyway, it has one end in infinite genus. Whereas this one that's a reflected one, has genus 0. And that's not real obvious, right? Genus 0 means that every simple closed curve separates. And in both cases, in the first case, you have two, first case you have I said one in. This is not right. I think I said one in here. That's not right. You have an infinite number of n's, and you have what are called two limit n's. So that was wrong, what I said here. So the first case, you have one n. In this case, you have what's called you're going to have two limit n's. You're going to have an infinite number of n's on the surface. Somehow an infinite number of ways to travel infinity. We're going to look at this in a little bit. Okay, so now I'm going to kind of go into a different area, a different kind of question, another kind of problem. How do you decompose space into regions and try to minimize surface area of those regions, subject to some kind of breaking it into pieces? Okay, so we have this surface kind of comes up in some of these questions. So you have this minimal surface. It's actually what's called triply periodic. So I can take this building block minimal surface and just translate it around in space, and I'll make what's called the Schwartz P surface. Okay, so it's in a minimal surface. There's lots of lines in it. And as I tried to mention before, if you have a straight line on a minimal surface, you can always extend across the straight line by reflection across the line. And reflection in R3 across the line is rotating by 180 degrees around the line. So you reflect across the line orthogonally, that's rotation by 180 degrees. So anyway, so we can imagine this forming somehow a foam, right? There's an inside and there's an outside region. So here are some pictures, very interesting. So, but it leads to a question posed by Kelvin. So you try to divide space into little pieces, like the Schwartz P surface, into little solid regions. And you want to partition it into cells of equal volume with least area surface between them. Okay, so that's the question. How do you do that? So it's easier to see in the plane. In the plane, we understand what the answer is. It turns out in 3 space, we do not know the answer to Kelvin's problem. It's still an unsolved question. How do you decompose space into cells? Say, fix the volume of the cell, and now I want to minimize the property that its area is smallest. I want to find that most efficient soap foam. Okay, think of foam. Okay, so anyway, in the plane we can understand. So we have these decomposition of planes, for example, triangles, squares, hexagons, right? Okay, which one's the best? Which one has the least perimeter per area? So you fix the area of these pieces, and the answer, I guess most people already know, the answer is the hexagon pattern. It solves this sort of an isoparametric type problem in the plane. Very neat, very nice solution. So Kelvin said, well, I think I know the answer in 3 space. Okay, so he asked the same question in 3 space. Okay, so here was what he guessed was the answer. This is Kelvin's honeycomb. Okay, so it's not, anyway, so you take that sort of figure on the right-hand side and you chop off pieces of it and you stick them together. Okay, so that was his suggestion, and people thought maybe he had the right answer. Okay, so he's guessing that's the answer, and it's not the answer. It doesn't mean we know the answer. It's one of these problems. We know that's not the answer because we can find a comparison example. So we can find an example which does better. It doesn't mean it's optimal, right? So this example was found pretty recently, 1993. Here we go. It's a certain shape. They fit together. They decompose space into a little bit smaller surface area when you fix the volume. Okay, so now we're getting to these isoparametric questions, and the natural realm of study of surfaces is constant mean curvature, not necessarily zero mean curvature. So we're going to talk a little bit about surfaces where the mean curvature is not necessarily 0, okay, but it is constant. So remember, those are called H surfaces. And we want it to be a critical point for the area function with respect to compactly supported variations preserving volume. And what that means is there's a notion of signed volume. So I'll just draw it like a curve in the plane. Okay. All right. Okay. So, what you want to do is during your variation, you want to preserve. If you did this in the plane, this would be you want to be area preserving variations. So you have a curve in the plane. Then you want, as you move the curve on one side, you want to get the volumes to always be the same, at least the first order. So as you move here, you want to push just as much this way as you're pushing this way. So the volume of maybe something else, like a cone on the thing, doesn't change. So the cone on the surfaces, the surfaces don't change. So in particular, if you are minimizing, if the surface you have minimizes in the space, it bounds a region, like the sphere bounds a region in space that's finite, then if you found a surface with least surface area for a given volume, it would not only be critical points of volume preserving deformations, it would be a minimum to volume preserving deformations. You can only increase the area if you do a deformation. You can only possibly increase the area. You can't decrease it. And of course, there's always a relationship between the sort of compactly supported variations and the local question. So if you have a constant mean curvature surface, when you go very, very small, then it turns out it always minimizes locally this sort of problem. It's not just critical points. Critical points in the big for compact regions, but in the small, this always means locally soap bubble. It's physically stable with respect to its volume preserving deformations. It minimizes when you go locally. So classical example, sphere, which is absolutely area minimizing for a fixed volume, bounding a fixed volume. We have cylinders. We have other surfaces of revolution called Delaunay surfaces. Okay, so maybe I've been talking a lot. Anybody have any kind of questions about anything? I'm talking like I'm an actor in a film. Okay, so we have these two contrasts: soap film, soap bubble. So you could think of making other soap bubbles. If this was not a round circle here, you just suppose it got bent, it got melted a little bit in the heat. When you blew a soap bubble, it would no longer be a sphere, but it would still be constant mean curvature. It would still be local area minimizing with respect to some volume constraint. So okay, so that's what we call these. Okay, so here's kind of a neat picture, and I'll talk a little bit about this blue surface is actually going to be kind of interesting to us. Okay, so this is a doubly periodic. Means it's invariant under translation in two orthogonal directions, like under Z cross Z. So you have the surface in R3. It's basically made by taking two planes and then connecting them by catenoids. So imagine there's sort of a top blue plane, a bottom red plane, and then you, in a periodic way, you connect them by catenoids and then perturb it a little bit. It has constant mean curvature. In fact, not only does it have constant mean curvature, I can do that so that surface lies in a slab of arbitrarily small volume, and the mean curvature is 1. It's hard to imagine that. So I can put it's infinite genus surface. I can think of it in a torus. It's got finite topology in a torus. But I have this sort of blue surface on the left side, and I can have it have constant mean curvature 1 and yet be in slabs of arbitrarily thin slabs. Okay, so in that case, of course, to be contained in a small slab means the second fundamental form must be really big some places if I'm going to do that connection stuff. So this is going to have very big second fundamental form, but its mean curvature could be 1. Here's a more standard example. These kind of things come up in polymer science, where they mix two materials for various physical reasons or constrained to form a triply periodic pattern. So you have one material on one side. It wants to pull together, and another material, maybe a liquid on the other side, okay? And for electrostatic reasons, they want to form triply periodic patterns, okay? So these kind of things actually occur when you do certain experiments. You see this sort of material that's solid on one side and sort of a liquid on the other side, okay? And what again, they have surface tension. Surface tension wants to pull them tight, but they have volume constraints. So just like soap films, we have this sort of orthogonal forces pulling. We have the same sort of thing here. So it turns out surface tension creates these kinds of surfaces, okay? And the surfaces, when you can view them, for example, in a 3 torus, they're compact surfaces. There they may be stable. They may be, with respect to volume-preserving deformations, they actually are local minimums. Not global minimums, but local minimums. Okay, so that's why they occur in nature. There are reasons why we see these surfaces in nature, because they're somehow minimizing surface area or energy, which is proportional to the surface area. And so that's kind of the reason why we see these things. Okay, now if you see such a surface, constant-mean-curvature surface, then if you intersect it with a little ball, so if you look at either one of these surfaces, and you intersect it with a small ball, think a very small ball, what I see is a disk inside of that ball. And that disk separates the ball into 2 regions of volume. So we have a volume 1 here, a volume 2 here. When I make the ball small, because it has constant mean curvature, this surface will represent a surface of least area that has a separation property and has the given boundary curve. So just because it has constant mean curvature. These surfaces on the right-hand side, if they come from a physical experiment, have a global property. At least locally, they minimize the area subject to the volume constraint. But locally, they always globally minimize with respect to boundary values when you make the ball very, very small. So, okay. And then, of course, for gases, when you have like soap bubbles, make a soap bubble just means the pressure. Okay, so when you have a soap bubble, so here's our soap bubble, you have these molecules on both sides, right? And because it's surface tension wants to make it pull tight, try to be zero mean curvature, but maybe the pressure here, you have more molecules on the side. So they exert a force that pushes out. So if, for example, you have a piece of plastic, and then you have a piece of plastic, and then you put it in soapy water, and you put a bubble in here, then this surface here will have more pressure in it than it will have outside, right? It's kind of like, I don't know how to say. Think of this as also something you could blow air in. You kind of blowing air in this side, you'll get but a bent curve, you'll get this soap bubble. So when you have constant difference of the pressure, you get constant mean curvature. Stable constant mean curvature surfaces. So that's, again, a physical thing that's nice to think about. Not area, but pressure. Okay, because the force is proportional to the area. When the pressure due to the gas is proportional to the surface area. Okay, so this leads us to these really nice questions, which hopefully, who knows, maybe we'll solve some of these this summer. Okay, so isoparametric domains, you could talk about this in a 3-manifold. You have a 3-manifold like R3. An isoparametric domain means you fix a volume, like 1, and you look for all smooth domains that have that volume and are compact, and you look for the one that has the smallest surface area. And that's a question. Well, you could ask, do such things exist in general? Do there exist solutions? And once you find solutions, what are regularity properties for the boundary of the domains? And to what extent they are unique? What can you say about their topology? You can ask lots of questions. Okay, but anyway, the question is, fix a volume, and in a manifold, fix a domain which has least surface area for its volume. Okay, so as we progress through the course, I'll probably be talking about some examples of what are called homogeneous three manifolds. Okay, and a particularly nice collection of them are examples where you're diffeomorphic to R3. So we have R3, we have hyperbolic space, and it turns out we have lots of other homogeneous three manifolds. We can take the three sphere, for example. We have all these different, but I'm going to focus on the ones that are R3. Okay. Okay, so we have a transitive group of isometries. Okay. This conjecture says that just like in R3, isoparametric domains are balls. Those are balls. The boundaries are spheres. The second part says that, okay, right. I guess one can even conjecture, one way to see that this might be true, I think I gave my talk the other day, is that maybe it's true that closed surfaces without boundary that are embedded in constant-mean-curvature, maybe they're forced to be spheres. If they're forced to be spheres, since you're in R3, they bound balls. So this is really, there's a much more general question. So I'm just asking the simple question. When you solve this problem, do you get balls? But maybe the only domains which have constant-mean-curvature surfaces on their boundary, compact domains, are in fact balls. I mean, maybe that's the only way it can happen. So, but anyway, with respect to the problem, that's one question. Then the question is uniqueness. So in R3, we have a unique solution to the isoparametric problem. You fix a volume, you get a round sphere. Well, here's another solution. It's a round sphere, and I can translate one of those balls into the other balls. But what does translation mean? In fact, what does left translation mean? Well, in order for that to make sense, in other words, I want the summit to be left translation, I better have a Lie group structure, okay? So it turns out if you're homogeneous and you're diffeomorphic to R3, you are always a Lie group endowed with a left invariant metric. So you take the metric at a point and you left translate that metric. So not only are we saying that that we can get from one isoparametric domain to another one, in fact, they are not just that. We can do that by a particular kind of of symmetry, left translation. Not just any symmetry, but very special ones. Okay, so that's the question which we'd like to understand better. Okay. All right, so now I'm going to come back a little bit to minimal surfaces and uniqueness questions about minimal surfaces. Some very simple questions, the simplest kind of questions, and we don't know the answers to them. Okay, so it starts with this. Given a simple closed curve in R3, okay, does there exist a minimal surface spanning it? This is an existence question. And there's, of course, the question of uniqueness. How many does it bound? What do they look like? What can you say? Well, how much information can you get about all the examples? Okay, but we were just trying to find one. And so with respect to finding disks, these two guys solved the problem a long time ago. And our more important question is, what are the shapes? Can we write them all down? Given a curve, can we write down all the possible shapes? Well, when the curve's pretty complicated, when the curve's just a circle in the plane, of course, it's easy to understand. But here's the more complicated question. So I'm going to start this with a very simple sub-problem, which is not where the curve is connected. But I'm going to consider, for example, two curves, Jordan curves on parallel planes. And if we try to at least understand this particular problem today, at least in certain cases. So for example, it looks like a convex curve, could I have a genus 1 minimal surface, a soap film, or a minimal surface bounding those two kind of curves? So that's one of the questions we're going to be looking at. So we're going to actually at least understand this in certain circumstances. So the catenoid is one of our great classical examples. It's a surface of revolution by revolving this particular curve, which is one of the sort of pictures of a rope hanging or chain hanging. it follows that kind of curve. Okay, so that's so Euler kind of he discovered at least when you take something like this and you take a part, so it doesn't hang very far down, then that turns out to be a surface of revolution of smallest area. Okay, so somehow started with that. Okay. All right. Okay, then we have these other things. So I'm going to focus right now on this one, Schiffman and Schoen. So Schiffman proved something very interesting. Okay, so imagine we have these two concentric circles, a circle here and a circle here, just translates, vertical translates. Why is it true that a catenoid is the only soap film? Why is it the only minimal surface compact minimal surface that bounds those two curves? Okay. So Schiffman did a certain thing. He said, if I restrict myself to annuli, okay, then he proved that, kind of not directly, but very directly, but he proved that you get a catenoid. Rick Schoen had a different approach. He used the reflection principle, and he proved that if you take these two curves, then the surface has to have all of the reflective symmetries of the boundary. So the surface has to be invariant under all vertical planes that contain the axis of the two concentric circles. So, and we could maybe see some things about that later. But anyway, so that sort of principle, which is very standard, but somehow people hadn't picked up on it before, that really is the best way probably to see that you get a catenoid. You get lots of reflective symmetry, then you get a surface of revolution, and Euler and Bonnet proved if you have a surface of revolution, then you were a catenoid. Okay. So, but this leads us into another situation. Suppose I take the two concentric circles and I translate them a little bit. Then I'm going to get an annulus. So let me erase this. Am I speaking too quickly? What do you think? No, it's okay. So here we have one circle, but now I translate the other circle. And I look at the soap film that forms. Okay, it's no longer a surface of revolution, so there's no longer a reason for the in-between curves. I take planes in between these two planes. Why should that be a circle? Well, it turns out it is always a circle. Okay, but he didn't approach it that way. He said, what are all of the minimal annuli that are foliated by circles in parallel planes? He just said, I'll try to classify them. I'll try to get a representation for understanding these surfaces, and I'll write down some meromorphic information on some surface that turns out an elliptic curve, and I will write down examples of these, and I will show that all examples have this property. So if he got circles, notice there's a center of the circles, and he actually described the curve of centers of these circles in terms of elliptic curves. Okay? So he had a very nice explicit description of all the examples. And then Schiffman, he came along later and said, well, if I have an annulus, then in fact, if I have a minimal annulus bounded by two circles in parallel plane, it is foliated by these round circles in parallel planes, round circles. Therefore, by Riemann, they're parts of Riemann's surfaces. So we're getting closer to understanding what happens here. How many soap films are there? What do they look like? Well, they're part. If they're annuli, they're Riemann examples. In general, I have two of them. I have a stable one and an unstable one. But I can explicitly write those down in terms of complex analysis, in terms of complex functions. I can explicitly write down these surfaces. But if I'm not an annulus, if I have some topology, I still don't know the answer. So I don't know if I have a genus 1 surface bounded by two circles. I still don't, people do not believe that those examples exist, but they don't know them. And like I said here, I'm going to try to explain to you the proof of Schiffman's argument. I think we can understand the proof reasonably well Originally, I put down to be proved quinta-feira on Thursday, but I think that was a little ambitious. I think do that. But there's a good chance I will be able to do this on Thursday. We'll see. We'll see if I get that far. So another question here. Suppose the curves are not circles, but they are convex, simple closed curves in parallel planes, two parallel planes. Then the claim is there are at most two minimal annuli. So when those are circles, we can do that by classification. You have Riemann's examples. But in general, if they're just convex curves, how many minimal annuli are there? It turns out there are only two. And you can say more about them. You can say there's either 0, that's possible. If the curves are too far away, there are none. Or maybe there's 1, or maybe there's 2. So it turns out if there's 1, then this example is called what's called stable, unstable. So yeah, it's a soap film annulus. This is in the case of convex curves. Stable, unstable, but it's weakly stable. If you just move your hand a little bit, it disappears, it pops. So it's weakly stable, pops. In this case, you have one. If you have two of them, then there's one stable and one unstable. So hopefully, in this index 1. When we get to doing this, I'll explain why. I think it's fairly easy to understand why that's true. Maybe all the rigorous proofs are a little cumbersome, but it's really understandable. I'm guessing, I don't know if Harold understands it real well, but I think you all will probably understand it maybe even better than me by the time we get to it. So we'll understand why it's true. Why is there one stable one index 1, 1? Okay, we'll try to make sense of that, even if you don't know much about what stable index 1 means. Okay, so we're going to do this pretty soon. Okay. Oh, another thing is, when you have an annulus, then all the levels, and this is convex, then you also want to prove all the level sets are also convex. And that's pretty easy to prove. Harold showed me how to do that a number of years ago, so I'll basically explain why that's true. It's pretty simple. Hopefully, I'll get to that pretty soon. Okay, so what is Riemann? So how do we get Riemann? Again, think in terms of soap films, stable soap films. We have a catenoid soap film. We shift the curves to the side. Then by Schiffman, I am foliated by circles in every plane. Okay. Well, in any case, when you have analytic boundary data, so a circle is an analytic curve. When you have an analytic curve, the minimal surface that glues onto that analytic curve always lies in the interior of a bigger surface. In other words, there's a bigger analytic surface that's a soap film. So when you have a soap film and you have the boundary is an analytic curve, it's actually inside of a bigger soap film. It's actually, you have this what's called boundary regularity. You're actually inside a bigger analytic surface. Okay? So since circles are analytic, that means when I shift, I can extend the surface a little bit. Well, it's foliated by circles. So that property also holds for the bigger surface. And just keep on going. Circle, 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 circle. Well, it means it's foliated by circles. However, the radius of the circles that you get as you come up. So we're foliated by circles, okay? We keep on going, right? It's analytic. It just keeps going. Circle, circle, circle. But the circle can actually have infinite radius and finite time. So imagine these circles. The centers of the circles are going off kind of along this green line as you go up, and they have infinite radius and finite time. And then I get a straight line. But if I have a straight line on a minimal surface, again, I can rotate by 180 degrees around the straight line and keep going. So I get this interesting surface. And so in particular, I'm going to get a line here, and this is actually a building block. If I translate this way, I can extend the surface. That's an orientation reversing translation on the surface, but anyway, it's invariant under translation. So these examples of Riemann are actually periodic, and we'll probably see better on another day exactly what, more about their topology and some other things. So we're going to see a little bit about that today. So here's actually a nice computer graphics picture by Matthias Weber. You can really see it. This is perfect, right? Yeah, I can see the circles. I see the straight lines, okay? And what is the family? I can tell you the entire family of Riemann examples. That's pretty neat. So let's just go through that again. What is the family? Well, at one end, I start with a catenoid, which is not really a Riemann example. It's somehow a limit of Riemann examples. And I just take it, so I take the two curves, put them pretty close, translate them to the side a little bit. That's one parameter family, and now bring them down. So you translate them, translate them a little bit more. So you translate them, and now you bring them down to each other. Right. And when you bring them all the way down to the plane, the subfilm degenerates into two moons, two half sort of moons, sort of like, see the two pieces planar domains here. That's what happens to the subfilm. And you could say, well, what happens as I got very near this singular limit? Well, it's not hard to see. When you homothetically expand, this circle becomes a straight line, right? You kind of try to make the distance be the same. This goes to a straight line. You start seeing a helicoid. So when you have subfilms on wires in different planes, and you bring them down, and the final examples intersect transversely, right before you get there, what you see on the surface is a little helicoid. Okay? So these surfaces, if you do them correctly, they also yield helicoid limits. So in one limit of the parameter, when there's concentric catenoids, and then the whole path goes down to connect up with the helicoid. Okay, this is just, again, a picture explaining what is genus 0. So this says that the genus of all these surfaces is 0. We'll see that in a minute. But what is the genus of a surface? And we're going to be talking quite a bit about this. This is a nice picture I made for some other talks, so I stuck it in here. So we have surfaces. They might be the same. This is a sphere. That's a sphere. A sphere is genus 0, meaning that every simple closed curve separates. Okay? Genus 1 just means there is one curve. You can find curves that don't separate, but you can't, if you find two that are pairwise, they're disjoint from each other, then they have to separate together. Genus 1 means two simple closed curves that don't intersect, in fact, always separate. That's what genus 1, and you keep on going. So the genus is the maximum number of pairwise disjoint simple closed curves that don't separate. So here, for example, 1, 2, 3, 4. If I put any other curve on that surface that's disjoint from the blue curves, it will separate it. Can't put 5. That's the idea of genus. Okay, so here is the one of these big theorems. Right. Now, we have an adjective there which we'd like to remove. So we're looking at what we call properly embedded surfaces. So if you remember this idea where we're looking at proper surfaces, that just means in a big ball, we see a compact surface. We see a compact part of the surface in a ball, so a finite area inside of balls. Okay, so properly embedded. Embedded means doesn't intersect itself. So we have these sort of examples. You have the catenoid, you have the helicoid, of course you have the plane, which is not very interesting, and you have the Riemann examples, and the theorem says that this is the entire moduli space of genus 0 examples. So this is wonderful. Not only do you have, the moduli space is a curve, you have somehow explicit representation of every example. You can make these beautiful pictures that Matthias did. I can make an example for everything. And you can also think of what's the natural way to parameterize these surfaces. It's another question. And depending upon how you like to think of parameterizing, you get other sort of interesting results. So here's the other interesting result. Now, if you noticed, when I did this moon picture, so I take the two curves, I translated them continuously, The soap film just moved as I did that in a continuous way. Then I just vertically translate down. I converge to this picture. So think of fixing this distance between these two intersection points to be distance 1. Okay? Then what I see forming on the Riemann examples are two helicoids that somehow get glued together with very flat horizontal parts of the surface, right? Remember, this is only a compact, somehow, part of Riemann. Remember, I have all these planes, these very flat parts. So I'm actually going to turn out to converge to a foliation away from two vertical lines. So I'm going to see helicoids forming on Riemann, separated by essentially distance 1, if I did this particular deformation, and the surfaces themselves converge to a parking garage structure with two columns. So I converge smoothly to a foliation by horizontal planes away from two vertical lines. That's how things happen. And this sort of property is ubiquitous. It appears everywhere in the subject. At least when I'm looking at the subject, I see this happening all the time, at least on certain what are called scales. So this is a very familiar structure, and we're still trying to understand this. There's work done by Matthias Weber and Martin Trezet, and they said, suppose I have a sequence of minimal surfaces and they converge to a parking garage structure. Where are the columns? I can't put the columns anywhere. It turns out there are special places where these columns appear. And they're related to Hermite polynomials. They're related to the zeros of certain polynomials. And anyway, it's very interesting, the sort of balancing conditions. How do you get something minimal converging to a foliation? And it's very interesting what happens. Okay, so here we have some of our crucial language. The vertical lines in the limit structure are called the columns of the parking garage structure. And the parking garage structure is somehow the limiting process. It's the foliation and together with how it converges to the structure. So anyway, it's something else. Okay, so now we're going to be formal. So we're going to have real definitions. So what does proper mean? We talk about properness when we talk about continuous maps between topological spaces. So suppose you have a continuous map from X to Y, and we say it's proper if the preimage of any compact set in Y is compact in X. So it doesn't usually help us very much. But anyway, that's the definition. And the surface is called proper in R3 if its inclusion map is proper. Okay? So it also comes back down to what does it mean to be a surface in R3? I think of an abstract surface together with a mapping, an immersion of the surface into R3. That's the way I like to think of a surface. I have an abstract surface and it maps into R3. If I have a surface in R3, it inherits a metric and an inner product on its tangent spaces, and that induces a Riemannian structure on the abstract surface. A Riemannian surface has its own intrinsic topology, where you take 2 points on the surface, the distance between 2 points is the infimum of the lengths of all curves that join the 2 points. That's the Riemannian intrinsic distance function. Okay? Now, it turns out that topology may or may not agree. The generated by that distance function gives you a metric space structure, which has a topology, which may or may not agree with the topology of the space you map into. Okay? In other words, it might not correspond to the subspace topology. So when it does, the mapping is called proper. Oh, right, no, when it does. So anyway, it's proper if that inclusion map has this property. Okay. All right, so what does it mean? So you can think, what does proper mean? In the case of surfaces, it means if a surface is not proper, it means you can find a sequence of points on the surface which go to infinity on the surface. Somehow they leave every compact set of the surface. And yet, they don't leave every compact ball in R3. They have a limit point. So you have a sequence on the surface which diverges to infinity on the surface, and yet it accumulates in R3, okay? So this is the problem. So these surface points don't converge on the surface because they leave every compact set, but they do converge in the ambient space. This is the problem of being not proper, okay? And here's the picture for not proper curve in the plane. So think of the blue circle. That's nice and proper. It's compact. But we have these spiraling red curves and green curves which spiral into the blue curve. So as metric spaces, those red curve, think it's an infinite curve, is just the real number line, right? It's just the real number line. I'm mapping it into the plane, but it's certainly not proper. Because I can take a sequence of those red points, and they don't converge on the real number line. They go to infinity on the real number line, but they do converge to a point on the blue circle, right? And you can make surfaces by just taking that lamination. Okay, we're going to talk a little bit more about laminations another time. I guess not today, but we're going to have we've somehow decomposed the plane into a collection of curves. It's a closed set. We have a red curve, a green curve, and a blue curve, and somehow those are going to be the leaves of the lamination. So we have this lamination, and we cross product it with R. Then we have this over. So we just project, just cross product going out. You'll see a blue cylinder, and you'll see a surface just wrapping around the blue cylinder, a red surface and a green surface. So you can make the same sort of picture in R3. Okay, so those would be not proper surfaces. Any questions about this idea of proper? Okay, so now we're going to try to connect lots of these definitions that we have so far. In other words, things about topology, properness, and completeness. Okay, so reiterate, the genus of a surface is the maximum number of pairwise disjoint curves that don't separate, okay? So if the genus could be infinite, right? You could have an infinite genus surface, certainly. And somehow a description of it. What does it mean to have finite topology? So that is, again, a very popular vocabulary word in the subject. Harold, in particular, studies lots of times. Recently, for example, finite topology, minimal surfaces in hyperbolic three-manifolds. What do we mean when we say finite topology? One possibility is we're talking about closed surface. A closed surface meaning compact, no boundary. That's an example of finite topology. Finite genus, closed surface. But we could also imagine removing points from such a surface. That's also finite topology. And each time you remove a point, you add a factor of z to the first homology group, or a new generator to the fundamental group. So finite topology really just means finitely generated fundamental group. That's another way to think of it. Or by classification, we just take a closed surface and remove a finite number of points, up to homeomorphism. And homeomorphism is pretty weak. Diffeomorphism doesn't make any difference. But sometimes we're interested in conformal structures. So we'd like to know, is it conformally, somehow if we had a surface with a metric, is it conformally have that property? And planar domain. Okay, again, we use different language. Sometimes I will say planar domain. Sometimes I will say a surface of genus 0. So when you're non-compact, genus 0, connected surface, just means it's diffeomorphic or homeomorphic to a domain in the plane. So by classification, genus 0 just means I can parameterize the surface by a domain in the plane. And we just classically, we say planar domains instead of genus 0. So that's a very important thing to keep in mind. Genus 0 just means, and connected just means we're connected domain in the plane. Complete, okay, complete of course means complete with respect to our Riemannian distance function. So once we have a Riemannian surface, we have a distance function on it. If it's a complete surface, just means that metric is a complete metric space structure on the surface. And it's related to geodesic completeness and other things which are useful for geometers. But it just means that the natural distance function on the surface is complete. And then we can relate these two. So if you have a properly immersed surface in R3, so you put surface in R3 so that it's properly immersed. So this mapping is proper mapping. Why is it always complete? Okay, and the reason for that comes back to a property. Certainly, let's see, so what does it mean to be proper? It means if you took a compact set here, the pre-image is compact. Where popular compact sets here would be balls, closed balls centered at the origin. So imagine pulling back the ball of radius 1 at the origin, the compact ball of radius 1. Well, that's a compact subset of this surface. And then you can see that the closure of the ball of radius 1 intrinsically on the surface is contained in the pre-image of that compact set, because intrinsic distances are always bigger than or equal to extrinsic distances, right? A curve on the surface that minimizes the distance between 2 points, if I'm in R3, maybe a straight line segment will do better. So I get an inequality. But if you're in a metric space where the balls of radius 1, the closed balls of radius 1 are compact, then you're always complete. Okay. All right. Okay, so in order to understand surfaces, it's nice to get sort of a Morse Theory picture of surfaces. And even more so in the theory of minimal surfaces, it's nice to understand how to make minimal surfaces inductively. So we're trying to make some kind of complicated surface. Maybe we do it in steps. We make a compact surface, and then we make a bigger compact surface that's somehow almost the same as one we made before. And we have a sequence of these. That's maybe how we make complicated surfaces, by taking exhaustions, somehow simpler surfaces, simpler topology, like finite topology, and then create these other surfaces. So this picture turns out to be very important in applications of existence theory, producing minimal surfaces that have a given topological property. So what does this picture correspond to? It's kind of like, think of a height function going sideways, and you have like a Morse function. You pick certain values, like integer values, okay? Or like the distance from the origin, for example. So I want to start off with a disk in the beginning, okay? Then in this picture, then I'm in this region between here, I have a pair of pants. In this region, I have a cylinder, or I see, which is a product, right? Cylinder is a product, not very interesting. Or I have a genus 1 surface. That's a genus 1 surface with two boundary curves. Similar kind of thing here. Between here and here, exactly one interesting thing. Not interesting, cylinder, a pair of pants. Okay? Two not interesting things up higher, an interesting thing, genus 1. And you keep on going like this. Now, it turns out that in this picture, every orientable surface has such a decomposition. I can take any open orientable surface, I can decompose it and find an exhaustion of this type. It's called a simple exhaustion. What's nice is when you go from one stage to another stage, only one interesting thing happens. Nothing interesting happens here. Something interesting happens here. And so here's a formal definition. He's filming it, and I guess that's fine. You can go look at it. I'm also going to have available all the slides, so you're welcome to. We can post it or something like that. So we can post this slide. You can read this at your leisure. The only thing that's different here is that when you go from one stage to another stage, here I have, for example, a pair of pants is interesting. Genus 1 is interesting. That's the only thing that happens when you're orientable. If you're non-orientable, I could have a Mobius strip with a disk removed. or I could think of taking two disks out of the projective plane. So I could have somehow non-orientable pieces appearing. So that's this right here. Could be a Mobius strip with a disk removed. Other than that, if for orientable, I don't have those, but for non-orientable, I do. And of course, when you get to, if you have finite topology, that means somehow it's finite, this process, then at some point, nothing interesting happens. So if I have finite topology, it means at some point, everything is not interesting. I still have these cylinders, these compact cylinders, but just nothing happens. It's just cylinder, 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 forever and ever. It's just not interesting topologically. But they're still there, and I still have the exhaustion. So that's what this is about. Other than that, it's just that picture. And then we have the theorem that every surface has that. So when we're trying to create minimal surfaces, for example, a nice theorem that I did with Ferrer and, let's see, anyway, friends of mine in Granada, we proved that you take any open surface, there exists a proper, complete immersion of that surface in the unit ball. Proper in the unit ball means it's not proper in R3, but in any subball of the unit ball, it's proper. It's compact. It's complete, it's proper in the unit ball. And you can say more things. But the way we do that is we use this decomposition. And we somehow imagine making a minimal surface in a ball almost of radius 1. And then a little bit bigger. And the topology, as we go from bigger balls to bigger balls, we add handles. We do one step at a time, we change the topology. So that's one of the reasons this is very useful. Okay, so of course, now we are coming back to the thing, this is kind of trivial, but cylinder, what's the topology of a cylinder? So you might have to think a little bit about it. A cylinder is also an annulus. An annulus lives in the plane. So this is a planar domain. In particular, by the Jordan curve theorem, it's genus 0, and it's genus, anyway, it's just genus 0. And topologically, we can also view it this way. It's a plane minus one point. Now, the plane is just the two-sphere minus a point, so it has finite topology. It's a two-sphere minus 2 points. A cylinder is a two-sphere minus 2 points. Okay. So I'm going to talk a little bit about classification of these surfaces. I'm certainly not going to get too far today. Then I'll talk more about geometry, and then I'm going to come back again and talk a little bit more about surfaces. So I think it's to get a little bit at a time is better than everything at one time. So we're going to try to understand what is the classification of surfaces. Okay. Well, closed surfaces, orientable surfaces, we understand. It's a sphere and you attach handles, so that's pretty simple. We're interested in non-compact surfaces, and the first case being genus 0. Can we really kind of figure out how to make every genus 0 surface? Okay, and I claim we can. And we also know how to do that from this previous picture, right? Genus 0 means that all of these, you never have any of these kinds of handles. All we're seeing are pairs of pants and cylinders. That's all that's going on. Okay. All right. Okay. So if you have a genus 0 surface, then it can always be parameterized, parameterized by or diffeomorphic to the two-sphere, and you remove a closed or compact subset that's totally disconnected. So it has no curves in it. You can always do it that way. You can always remove a closed subset of the two-sphere. It certainly has genus 0. Okay, but imagine you can collapse curves to points, and it's just nice to think about not having any curves in it. So you can make them be totally disconnected. Okay. And that set, when it's totally disconnected, it can be identified with all the ways to travel to infinity. So in that very heuristic, the first point of view, what is an end of a surface or a manifold? It's just different ways to travel to infinity. How do we travel to infinity? We want to do that in a proper way, right? we don't want to keep coming back near where we started. So we want to do it with what's called proper arcs. So we look at an arc, it starts at it right here, and then I travel to infinity, right? So I want that arc to be proper. I don't want to keep coming back into the same compact set. It's not a very efficient way to go to infinity. So proper arcs are the way to. So we can identify in this setting the set. Every point in the set becomes a end of the surface. And notice E has a topology on it. It has a subspace topology. In fact, it's a metric space. Okay? And it turns out Hucky and I studied some things about ends of very general topological objects, like CW complexes and things. You can prove that the space of ends of a reasonable object, like a surface, is in fact parameterized or naturally homeomorphic to a closed subset of the unit interval. So even though this looks very, very bad, I could have picked E to be on a curve in the plane, on a great circle. I could have picked this very weird set to actually be on a curve. And then it becomes much more concrete to understand. Okay, and then what's the classification theorem? It says that two genus 0 surfaces with ends, the first one has ends E1, the second one has ends E2. They are diffeomorphic if they have genus 0, if and only if the space of ends, the E sets, are homeomorphic. Necessary and sufficient condition. So that really means we're in pretty good shape. We take a great circle on the sphere. In that great circle, we remove a closed set that's totally disconnected, like a Cantor set. And that's somehow how we make things. So the whole problem comes down to deciding when are two of these closed sets of a unit interval homeomorphic. That's a little tricky too, right? But you can understand it at least. Any questions? Somebody said something? Okay. Okay, so that's a nice result. And I guess this will be probably the last thing for today. Okay. Right. A planar domain with one end, then you're just, if you're genus 0 or if you're a planar domain with one end, it just means you're diffeomorphic to the plane. You move 1 point from the two-sphere. That's diffeomorphic to a plane. So we're talking about planes. If you remove 2 points from the two-sphere, right, then you are a cylinder. You're an annulus. You are a punctured plane. Okay, so those are also some language we have. If you have a finite number of ends, n, that's the same thing as taking the two-sphere, removing n points. That's all you have. Okay, like a cylinders, remove 2 points, or a plane, remove n minus 1 points. Now we get this interesting notion of limit n. So remember we had this closed set, which we can think as being, if we were genus 0, just being on a great circle on the two-sphere. That closed set is infinite. We always have limit points, right? Right? If you have an infinite set and it's compact, it always contains limit points. Those limit points are not just any kind of n. Those are called limit ends. And right, those are called the limit ends of the surface. So the limit points of the E set are called limit ends. And let's see, right. Let me just see if I can, all right. I guess I'll get to that picture and then we'll quit. Okay, so we have, right, if you took the plane and removed, say, the natural numbers from it, that would be, and we take the plane, remove the natural numbers from it. When we look at that on the two-sphere, what do you see? You see something like this. You see a sequence of points in the two-sphere that converge to the North Pole. So that's a set with one limit point. So that would be a genus 0 surface with one limit in. And right, so let me just go back. I don't think I have that picture here, so because that's going to be hard. Here's an example. Just do this one example. Remember I said before Riemann examples Parking garage structures that where you spin oppositely and you have two columns have genus 0 and two limit ends. So what does Riemann example look like? So what is this picture really? Topology for a geometer. Just look at this picture. I see an infinite stack of planes at integer heights, and I connect them up by little tubes, right? Well, planes have genus 0, and if I just connect them up, then I make a new genus 0 surface. I don't connect them up twice, right? So that certainly has genus 0, and in fact, we can actually see it's parameterized by a cylinder where we remove points at integer heights. Why is it a cylinder with points removed at integer heights? What is the intersection at every height? It's a round circle. Well, it's like a circle in a cylinder. But sometimes you say, I get to a line. Well, what is a straight line? It's just a circle with a point removed. So you have on the side here an infinite cylinder with points removed at integer heights. And a cylinder is planar domain, so and you remove more points, it's a subdomain. But we have a limit n at plus infinity. Each plane here, its end corresponds to a point on the cylinder. The cylinder has two ends, one at plus infinity, one at minus infinity. So Riemann has this sort of picture. It's the two-sphere with points that converge to the sequence of discrete points converging to the north and the south poles. So it has two limit ends. And we'll get to all the more complicated pictures next time, like Cantor sets events and stuff like that. So I think that's good for today. All right, so I don't know what to tell. Lucio, do you have any comments to make about how to present anything? Very good. I can give somebody, I don't know who I would give it to, but I can give certainly somebody the PDF file for like today's lecture, which is really probably 2 or 3 days lecture. Oh, to him, okay, good.
You mentioned about 20 unsolved problems. It would be really interesting to make a list of all these problems you mentioned.
Right, I do have a collection of conjectures.
Well, not just the conjectures, all the unsolved problems for the last 200 years also.
Right.
You mentioned about 20 today.
I mentioned lots of unsolved problems, right.
Have them written down on this paper.
Yes, and largely they are written down, and like in organized parts of this lecture came from that lecture about unsolved problems, like the convex curve questions. So yeah, so that's certainly doable. Yeah, right. And maybe at the very end of the course I'll summarize. I'll give a lecture and summarize. Remember we talked about these problems, or maybe the last hour of my last lecture. We can just summarize all these different questions. It'll be in a PDF file. Okay. Good, thank you. And I would like to get to meet everybody in the class. I know the people came earlier in the class, and then after the class actually started, another group came. They were probably in a different room, I guess. But I'd like to get to know everybody's name.
So it's good that you